let's say you have an invertible function f. So invertible, meaning the reverse when you flip around all the pairs, that's a function. And let's say you have x in the domain of f and y in the range of f. Then if you have f of x equals y, so if y is the output associated with the input x, then what do you think will happen when I take f inverse, I can call it the inverse since f is invertible, and I apply it to y? So probably it should undo the application of f and end me up in this situation, right? So let's just check that this actually works. To get to be able to even apply f reverse to y, we need to know two things. That f reverse is a function. Okay, check. F is invertible, so f reverse is a function. And the second thing we need to know is that y is in the domain of f reverse. Well, the domain of f reverse is the range of f, which we are assuming y is in here. So I am using Theorem 69 here, which tells us that when you flip around all the pairs in a set of pairs, the domain and range get swapped. So we can at least talk about this. Then to decide whether or not this really is the same as to decide whether or not f inverse of y really is the same as x, we should look at it in terms of the theorem called essence of evaluation. So up here, Theorem 51, if you want to say that one thing is f of another thing, then as long as you're looking at a function, then that's just the same as saying that a certain pair is a member of that function. So down here, this is equivalent to saying that the pair, let's see, y comma x, right, input then output, is in there. And this one is the same as saying, let me get this out of the way, this. So this is true because Theorem 51 applies whenever you have a function. And we're in a situation where f is a function and f reverse is a function. So this is the same as saying this is the same as saying this, and in fact these two are saying the same thing, right? That's sort of how reverse works according to Theorem 67. A pair is in a set of pairs if and only if its flipped around version is in the reversed set of pairs. So overall we have f of x equals y if and only if x is f inverse of y. So this shows you sort of in the language of function evaluation rather than in the language of pairs being members of things. This shows you in the language of function evaluation how the inverse of a function maps outputs back to the inputs that they came from. But this idea of mapping outputs back to the inputs that they came from, this idea only makes sense when f is actually invertible. Right? If f is not invertible, then f reverse, while being a thing, is not a function, and so you couldn't evaluate it anywhere. So if your original f were this sort of thing, something not injective, then f reverse becomes not a function, right? So you take this output, and then you're like, okay, let me go back to the input that it came from. Well, I don't know where it came from. It could have been either of these possibilities. All right, so what we just discussed here is Theorem 74, this idea that the inverse of a function, when a function is invertible, sends outputs back to the inputs that they came from. You'll find this to be useful when we do kind of algebra-like things with function evaluation. Like, say, you've got an equation, an equality statement, and you've got a function evaluation on one side telling you that f of this is that, then this allows you to, you can think of it as apply f inverse to both sides and then cancel the f on one side and up here. And that might help you solve an equation for one variable. Now, the idea of actually applying f inverse to both sides and having that cancel in some sense this idea is really more captured in Theorem 76, where if you have an injective function, remember injective is actually ends up being equivalent to just saying that f reverse is a function. It's equivalent to saying it's invertible. If you have an injective or invertible function, then when you compose f with f reverse in this order, then you get the identity. So there is a good reason, so we'll get to discussing this in a moment, but I just want you to pay attention to the fact that the composition only appears in one order. If you want it to appear in both orders, like this and like this, then you need the function to be bijective. So this is more the context in which people would refer to f as being invertible. If f is injective, if it's only injective and not necessarily surjective, then technically, yeah, it is invertible according to the definition of invertibility. But look here, if it's not surjective, when you flip those pairs around, when you take the reverse, you get a function but with a smaller domain than you may have wanted, right? If f originally mapped x to y, and f is injective, then go ahead and take the inverse. That will be a perfectly good function, but the domain is not going to be y. So it's when you have a bijection, when it's also surjective, that that inverses and composition behave as nicely as possible with each other. If you only have an injection, then you've got only this. You've only got this result, that the composition in one direction is going to be the identity. All right, so for the rest of this video, so what did we do? At the beginning of the video, we did Theorem 74 pretty much. We went through how to prove it. For the rest of the video, I want to talk through Theorem 75. And then in the next video, we'll work out Theorem 76 carefully. So here is the statement of Theorem, I think it was 75. So I just want to talk through this basically. And this should always be compared with that one presentation problem I gave you guys last time, Theorem 73. So Theorem 73 lets you assume that you have an injective function, and then it tells you that, okay, then when you flip it around, then you have a function, and the domain is the range of the original function. Here we're starting not with an injective, but with a bijective, more than just injective, a bijective function, and then when we flip it around, the range does not actually shrink. So if you want to prove this, we can start by assuming we have a bijection. Then it is an injection, right? It's an injection. So then by that previous presentation problem, Theorem 73, f reverse maps the range of f to x, right? That's because that's just using this one, basically. Then, since this is a surjection, since it's surjective, the range of f is actually y, rather than only being a subset of y. So we can restate this, replacing the range of f by something that it's equal to. So in fact, f inverse maps y to x. So that's great. So the surjectivity of f makes it so that when you invert it, the codomain becomes the new domain. Then we need to verify that f reverse is a bijection. So is this here a bijection? Well, surjectivity in this case is an easy one to check, since the range of f reverse is the domain of f, right? That's by Theorem 69 again. And the domain of f was assumed to be x, right? That's one of the three things that's being said when we say f maps x to y. So that's what's needed to say f reverse is surjective. or F inverse. I can call it F inverse. And then how do we know whether F reverse is going to be injective? So one way to know that is we know that if we reverse twice, then we get back to the original thing, right? So F reverse, or F inverse, has the property that when you take its inverse, you get F. And F is a function, right? That's what one of the things we're saying when we say F maps X to Y. F is a function. So F reverse has the property that its reverse is a function. And if you look back here, if you have a function like F reverse, so replace F by F reverse here, then its reverse, which is F reverse reverse, is going to be a function if and only if it, which is F reverse, is injective. So because this is a function and its reverse is a function, it is injective. That's by Theorem 72. So when you have a bijection, inverting works in the nicest possible way, is when you have a bijection. When you only have an injection, it's not as nice, due to this domain not being what you might want. And further, what we have seen here is when you have a bijection and you invert, you get another bijection.